Hello everyone, welcome to the 7th session of Electromagnetic Theory and Interference course. Today's session we will be looking into the vector calculus, which is the essential part of the electromagnetic theory. So we need to understand vector calculus is dealing with the differentiation of and integration of vector fields in three-dimensional space. So we already know what is field, right? Field is a function where a particular quantity is specified everywhere in a region. So in our normally a field will be varying with respect to space as well as time. So there are two types of fields. One is a scalar field and other one is a vector field. Scalar field will, for example, a temperature is a scalar quantity, right? The field associated with the temperature is a scalar field. And a vector field, for example, our electric field or gravitational force, all are vector field because it is going to assign a vector, that is both the magnitude and direction, to each point. So throughout the session we will be taking the scalar field as a capital V and vector field as capital A vector. So today's session we will be discussing only about the vector differentiation. Okay, so we are going to see about the del operator, which is a vector differential operator. So del is going to be it's a partial differentiation, dou by dou x into the corresponding unit vector along the x direction, ax cap plus dou y into ay cap plus dou by dou z into az cap. This is the vector differential operator in Cartesian coordinate. Similarly, I can write the del operator in cylindrical as well as spherical coordinate. Only these three standard coordinate system, which is a non-orthogonal system, are taken into consideration. In case of cylindrical, we know that we have to take the coordinates rho, phi and z, and in the differential operator we have to consider d rho, and for psi we have to take the radius also into consideration, so rho d psi and z, that is dz. So the differential vector operator turns out to be dou by dou rho a rho cap plus 1 by rho dou by dou phi into a phi cap plus dou by dou z into az cap. Similarly, if we write for spherical coordinates, it is dou by dou r into ar cap plus, here it depends on the radius of the sphere, so 1 by r dou by dou theta into a theta cap plus, here this azimuth angle depends on r sin theta, so 1 by r sin theta dou by dou phi of a phi cap. These are the del operators in all the three coordinates, and we are going to use this del operator to find four different quantities. One is a gradient that we will perform on a scalar field, so we will write it as del V. Del V is the gradient of scalar, and divergence we will perform on a vector field, so it is del dot, it's a dot product, del dot A vector. Curl is also operated on a vector field, so it is del cross A vector. Whereas Laplacian, if I take, we will operate it on a scalar field, so it is a double derivative, del square V. Del V is a gradient, whereas del square V is a Laplacian. Dot product of the del vector and the vector field is divergence, whereas cross product of the same is a curl. So today in this entire session we will be focusing on only the gradient and divergence, and we will do one small problem there. So what do you mean by a gradient operator? For example, consider a situation where inside a room there is one AC. So if you be closer to the AC, there will be a region where there is a fast cooling, and when we go away from it, there is a region where the AC cooling will be less. So how will I, this is scalar because it's the AC means we are going to measure the temperature of the room only. Even though the temperature is a scalar, I can measure the rate at which the temperature is changing and in what direction it is changing. So this I can measure using the gradient operator. So gradient of a scalar field is a vector, so final result will be a vector only. Okay, that represent both the magnitude and direction of maximum rate of increase of V. Okay, V means is a scalar field. So if I write in a Cartesian, that is del V is equal to dou V by dou x into ax cap plus dou V by dou y into ay cap plus dou V by dou z into az cap. So what we have done, we have taken the del operator and I have just substituted the scalar field V in all the parts. Okay. So similarly we can write it for other two coordinate system, and we will see in detail in a separate video how to write these equations, especially the gradient, okay, and divergence as well as curl operation that we will discuss in other sessions in the other two coordinates. So where we need this gradient operator to be done, I want to see how my scalar quantity is changing and in what direction it is changing. In that case, I will apply a gradient and find the result. So even though if I apply the gradient on a scalar field V, my answer will be a vector, because if you see the function is differentiated partially with respect to x and it is multiplied by the unit vector across each of the directions. So let us understand by applying it in a problem. So the question given to us is one scalar function V. Okay, in this problem, the scalar function V is given as e power minus z sine 2x into cos hy, and we are asked to compute the gradient of this particular field. So we know the formula of gradient, right? Del V is dou V by dou x into ax cap plus dou V by dou y into ay cap plus dou V by dou z into az cap. So what is the meaning of dou V by dou x? We have to take the whole function and partially differentiate with respect to x for the first component. So if you differentiate with respect to x, other two components are constant, so it will be retained here. E power minus z cos hy is there, but differentiation of sine 2x will give me 2 cos 2x. Okay, and you have to multiply with the unit vector ax cap. Similarly for the second term, I have to differentiate with respect to y, right? So in that case these two terms will be there as it is. E power minus z sine 2x will be there. Differentiation of cos hy is sine hy, and that I have to multiply with the unit vector. Whereas if I take the last part, that is the differentiation of the scalar with respect to ez, so with other two components will remain same. Sine 2x and cos hy will be there. E power minus z differentiation is e power minus z into this constant minus 1 will be coming. So this plus and minus will be now turned into minus, into I have to multiply with the az unit vector. I hope you understood. Now let us move to the second differential operator, that is divergence. So before moving to the divergence operation, that is del dot, we will physically understand what it means. So if there is consider a tub where there is a tap attached to the other end, and from the one end the water is flown, okay, from a bottle or a tumbler. So if you see where the position where the water is poured, the water is increasing, okay, and in this region where the water is coming out of this particular tub or tank, the water is decreasing, and here is a region where there is a constant flow of water. So if I want to define a divergence, I have to define a divergence for a vector quantity only. So divergence of a vector field A, okay, how can I define? It is nothing but outward flow of any quantity. Okay, so here they have taken it as outward flux per unit volume. So we are defining the outward flow, that is outward flux per unit volume. Okay, so how to define it is the dot product I have already mentioned, dot product of the del operator and the vector field. So del dot A vector, how will I compute? We already know what is del, okay, and we know A vector. So if we dot product this del into the vector, okay, A vector, what answer I will get? So d by dx in dou ax by ax, that means dou by dou x into this ax component will be there, because dot product of this unit vector ax and this unit vector ax will result me 1. Similarly the other next to component, rest of the components, since this dot product will give me 9 values, out of which 6 will be 0, because dot product of different unit vectors will give me 0, but same unit vector I will get 1. Okay, so dou by dou x into ax component plus dou by dou y into ay plus dou by dou z into az. Hope you understood the divergence. So what will be the result of the divergence operation? I will get a scalar as output, because I have, see, there is no unit vector present in the output expression, whereas I am giving the vector as a input, I am getting a scalar as a output. Okay, this is one of the inference. So I can define 3 different divergence. One is positive divergence, other one is negative, and finally a zero divergence. Zero divergence in the sense what we understood from the constant flow of water. So see here, there is a point we have considered, and in across the point how the vector field is flowing, that is zero divergence. And when the divergence will be 0 also, we will see in the upcoming sessions. So now let us see, this is a point where there is a positive divergence. So the line vector field lines are coming out. That means this positive divergence indicates there is a source or a charged particle is present, whereas negative divergence means the field lines are coming towards it, so it is a sink or a load point. Okay, so as I mentioned earlier, the vector field is so the divergence is going to be 0. That means there is no divergence when, if my vector field is solenoidal. If the vector field is solenoidal, del dot A vector is going to be 0. This is one of the important thing you have to remember. We have defined the divergence for the Cartesian. Similarly, I can define it for both cylindrical and spherical coordinates. These things we will see it separately, how to write the expression. Okay, and now let us take one problem and understand how a divergence is computed. So they have given a vector field. How I am identifying it as a vector field? Because the unit vectors are represented along with the function, given function. So how will I define del dot p? It is dou by dou x px component. So this is the component along the unit vector px. Ax, I have the px component, and here I have the pz, but py component is not there. Okay, it is not present, so only it is 0 written here. I am just substituting the individual components. So if I differentiate dou by dou x with respect to px, first only this term, I have to keep y and z constant, differentiate partially with respect to x, I will get 2x, and this is going to be 0 because py component is not present here. This py along the y-axis I don't have in the given expression. Whereas if I differentiate the last component, that is pz with respect to z, okay, with respect to z means this turns out to be 1, whereas x will be there. So x into 1 is x. So I think you are able to understand, we got a scalar as a result, right? So today's session we discussed about the vector differential operator and how to compute gradient and divergence along with a worked out example. Hope you enjoyed the session. Happy learning. We'll meet you later. Thank you.